Oh, um, I'm really late today. Huh. 17 and a half hours until the next one. Okay. So, um, yesterday was easy, I guess. So let's see what today's is. Has anyone had a go at it? Hello, Maro. Hello, Smap UK. This one took me way out of my comfort zone, learned a lot. Oh, okay. Today is harder but good for Game Maker. Interesting. Maybe some sort of physics simulation or something. All right. Day 10. Ooh, mazes. Right. All right. Let me grab my coffee. Okay. Pipe maze. And generally good with the 2D maze ones. Well, we'll see. Pipe maze. So you use the hang glider to ride the hot air from Desert Island all the way up to the floating metal island. Oh yeah. We're on the... Okay. We're on the metal island now. This island is surprisingly cold and there definitely aren't any thermals to glide on. So you leave your hang glider behind. You wander around for a while, but you don't find any people or animals. However, you do occasionally find signposts labeled Hot Springs. Ah. So we've got the wiki to Hot Springs now. Okay. Cool. Pointing in a seemingly consistent direction. Maybe you can find someone at the hot springs and ask them where the desert machine parts are made. The landscape here is alien. Even the flowers and trees are made of metal. As you stop to admire some metal grass, you notice something metallic scurry away in your peripheral vision and jump into a big pipe. It didn't look like any animal you've ever seen. If you want a better look, you'll need to get ahead of it. Scanning the area, you discover that the entire field you're standing on is densely packed with pipes. It was hard to tell at first because they're the same metallic silver color as the ground. You make a quick sketch of all the surface pipes you can see. The pipes are arranged in a two-dimensional grid of tiles. It's got vertical, horizontal, L for north to east, north and west. Oh, I see. Dot means ground. S is the starting position of the animal. Based on the acoustics of the animal scurrying, you're confident the pipe that contains the animal is one large, continuous loop. For example, here's a square loop of pipe. If the animal had entered this loop in the northwest corner, the sketch would instead look like this. Yeah. In the above diagram, the S tile is still a 90-degree F-bend. You can tell because of how the adjacent pipes connect to it. Yeah. Unfortunately, there are also many pipes that aren't connected to the loop. This sketch shows the same loop as above. So... Alright, well that's not that bad because these don't even connect. So you would already know immediately that's going to be a 90-degree bend. But if they did connect, well, then it wouldn't be obvious, so you'd have to follow the loops. In the above diagram, you can still figure out which pipes form the main loop. They're the ones connected to S. Pipes those pipes connect to, pipes those pipes connect to, and so on. Every pipe in the main loop connects to its two neighbors, including S, which will have exactly two pipes connecting to it. Yeah, okay. Okay, this one. I mean, again, that should be 90-degree, right? If you want to get out ahead of the animal, you should find the tile in the loop that is farthest from the starting position. Because the animal is in the pipe, it doesn't make sense to measure this by a direct distance. You need to find the tile that would take the longest number of steps along the loop to reach from the starting point, regardless of which way around the loop the animal went. In the first example with the square loop. Yeah, okay. Find the single giant loop starting at S. How many steps along the loop does it take to get from the starting position to the point farthest from the starting position? Alright, so once we find the loop size, we can just reason that. We can just get that, can't we? So really just breadth first search to follow loop, depth first search even. There's not much branching here. I mean, there shouldn't be any branching according to the rules. We just... Where's S? Hang on. There it is. Alright, so we already know what S should be. It should be an F, because it would connect this J on the right and this vertical pipe here, but I mean it couldn't connect to these two, so S should be an F. We can just do that by inspection, we don't need to alright, so just looking at this, is it all consistent? Are there any pipes that go into... Yeah, look here, L. This one goes up and right, but that's a vertical pipe, so... So it's not always consistent. Sometimes pipes crash into each other. Okay, but it doesn't matter. We know the loop will be consistent, so... Right. Just copy that in. So first let's just pause the input. So we want to turn this into a graph, basically. Let's say yes, let's do an edgeless graph. So okay, define Gonna do a class graph. Define init self dot edges equals let's say just a regular dictionary. Fine. Add edge from U to V. Self dot. So these are basically no. See, I was gonna make this a undirected graph. So if a node connects to another node, then that second node connects back to the first. I shouldn't do this because that will probably interfere with the loop. Some other pipe might connect to it and make it connect to them, which is wrong. So no. So this is a directed graph. So we need self.edges. Hang on, let's use a default dict. It's always cleaner. From collections import default dict. So default dict is just a dictionary, but if a key doesn't exist in a dictionary, then it assumes it just defaults to a sensible default. In this case, we can tell it to choose an empty set as the default. So here, do that. So if U was accessed before it ever was in the edge list, then it will add U to the edge list, but U will just be mapped to an empty set. So self.edges U.add B is what we want here. So it will default to be empty set to begin with. All right. U and V, what are these? These are two-dimensional positions vectors, so we probably want pos class. Just say we don't really need to work out distance, like Hamming distance or Euclidean distance or anything like this yet. But we do need hash method because otherwise we can't put it in the set. So we need to define equal. Okay, that's fine. So these pauses we'll put in there. Is that all the prep we need to do before we start actually doing stuff? Amaro, you said you reused most of day 3's code. So was day 3 the one with the Oh yeah, this is the one with the gears. I probably don't need to reuse any of that if I'm going down this approach. Okay, so all right, now we can parse the input. So let's say was the same 140 size. Oh, right, okay. So here we want to look at each. Oh, okay. Let's say for I line in enumerate dot read lines, because we need to know the row number, for j car in enumerate line dot strip. Has Captain Coda already does his, or I guess he might be starting right now or even soon. We'll find out later when I finish the stream. Maybe I could raid him if he's still going. All right, so okay, so the pause is gonna be all right. Let's just do pause in terms of row and column instead of X and Y. Then I won't make any mistakes by mixing up the two, because X, Y, you normally think of X first, but then row and column, you think of row first, so. See, I've already got it. I already got it wrong here, look. It was, yeah, row and column there. Oh, no, that's fine. If we do this, it's consistent, okay. So that's going to be row, column, okay. Normally starts in about 20 minutes. Maybe this is a good time for me to actually, good time of day for me to actually start the problem each day. I don't know if I will though. I would like to go a bit earlier, maybe about 2 hours earlier. Normally. Alright, pause equals, so in this case it's going to be IJ. Alright, so that's pause. Alright. Okay, so we need to... So I can cheat and write just... No, I know what S is supposed to be, but we could write code to just infer it from the graph, just to complete, just to make our program work on any input. It would be a nice thing to have. How would I do that? I would have to... How would I do that? I would have to look at each... Okay, we look at each of the 4 neighbors, see if they have edges going into me, into the S location, and make those edges bidirectional. Okay. Yeah, that's not hard. Alright, anyway. Another nice method we should prepare is define get neighbors. But we don't want to go off the edge of the map. No, wait. Get neighbors. We don't need that. That's literally just the, that doesn't need to be a pause method, no. Alright, so, because it comes out of the graph, and it's cleaner, it won't go off the edge of the grid. Alright, so, basically we need to check for each kind of character. Leaderboard took 36 minutes to get full today. Interesting. I mean, part 1 is the kind of thing which I know a lot of competitors just have pre-prepared code for. Like, see, all this stuff I've written, that's just duplicate code I've written before countless times, especially for coding game. So it's mostly just, you'd have to write some sort of if-else for each of the different characters. And then it's just standard breadth first search, which people would have pre-prepared code for. So part 1, I'm pretty sure that can be done within a minute or two, I would expect. Part 2 must be harder then. Alright, we don't want to lose any information from this graph because I think part 2 might involve stuff outside of the loop, maybe. So, don't know how to get started. Okay, we just need to just go if R is S. Alright, so we're gonna have to keep this knowledge. Animal equals pods. Alright, let's go through each of them one by one then. So it's, I'll go in the order on the website so we don't... Alright, so we've got vertical pipe. I still don't know BFS or DFS. I was a business developer, always end up inventing them from scratch when I need them. I mean, that's pretty cool. Depth first search is the easiest to invent from scratch. In fact, in a lot of cases, you don't need anything beyond depth first search, but although breadth first search will give you the distance, which we do actually need here, so we probably should use breadth first search. Well, depth first search will give us... I'll think about it. Yeah, breadth first search I think is actually what we want. Alright, so car equals... Alright, starting with pipe. But yeah, depth first search is the most intuitive because depth first search is what you do when you're in a maze, like physically in a maze in real life. Well, it's the common method people use intuitively when they're playing a video game or in a maze in real life, and like in a castle grounds or something. Hampton Court Palace in the UK, if you've ever been there. That was my first experience of an actual hedge maze. Usually the best method is to turn every left, and then when you're going backwards, no, keep turning every left. That will get you back to the last junction and then take the next left. That's depth first search. Right. You have been to Hampton Court Palace. I went there on a school trip. So we need to connect. We need to make a graph here. You're originally from London. Nice. I worked in London for a couple of years, but I didn't enjoy working there. I gave up after a while. It's not my kind of place to live. I much prefer the quieter, more countryside-like places. But I used to work for Amazon in London. Going back, I wish I had picked the Cambridge office for Amazon, actually. That would have been nicer. Not much cheaper, but it would have been nicer. Alright. G dot add edge. So we got to go. So it's going to be I minus 1. No. It's going to be so we connect to I minus 1 J so in all cases we're usually going to add 2 edges, so and then we want I plus 1. Okay, so we're gonna have to do this a bunch of times. I used to work for HP. Alright. What role were you doing there? Job role. So we got 3, 4, how many? 1, 2, 3, 4, 5, 6. We can skip ground because that's... Alright, so 1, 2, 3, 4, 5, 6. Okay, let's get through these. Horizontal pipe. So that's I... Alright, and then we got L. It's going to be I minus 1J and I J plus 1. J north and west, so it's going to be north and alright, make sure we don't get any of these wrong because it'll be hard to debug. Started as a programmer whilst at university, ended as a software architect out of HP Labs with the fancy title of engineer scientist. Nice. J minus 1. Okay. And then 7. Yeah, there isn't an easy way to do this quickly. I'm sure a lot of the people who did part 1 really quickly still would have had to... There's probably some clever way of unpacking it quickly, but... You can do for delta in -1, the range -1 to 1 for I's and J's, and then just put the put these letters in the right order in a string or something clever like that. I J minus 1 I plus 1J. I did that in a single line. Oh really? Like a really long line, or you just had a really clever way of unpacking it? F By the way, Umara, I did my Doom run yesterday. All 5 hours of it. I did pretty well, actually. I got to episode 3 out of the 4 chapters of the 4 episodes of Doom. I got to level 6. The YouTube video took me many hours to upload, but it will be up today. It'll be better quality because Twitch will look horrible because of the bitrate. Doom bitrate will be absolutely demolished by Twitch because of all the fuzzy textures and stuff. Draw sprite asset index. Okay, it's game maker stuff. Did this on a previous AOC year. Yeah, a lot of this. Like I remember there was minecart problems which were very similar to this. They had tracks which minecarts follow. So some of the characters, well, the characters are different, but yeah, the principle's the same. F, so it's going to be I, J plus 1, I plus 1, J. If it's dot, we can ignore that. And if it's S, we don't know yet, so we'll have to fill that in. We want to use the minecart crashing. Yeah, that was an interesting problem. I made a big mistake there, which was using strip. So always, pretty much by instinct, I add strip online. The one case you don't want to strip is when the white space at the left or right is actually part of the input. So in that case, you had like a bunch of white space here, for example, but that needed to be retained because it was actually relevant, sort of. Or at least you would create situations where you would come down and you're missing part of the map. Oh no, actually on the right it doesn't matter. On the left it matters, because if you delete all the white space, then everything gets shifted. So yeah, that was one case where you don't want to strip. The only case I can think of where you don't want to strip white space off the line. Strip takes white space from the left as well as the right. That's something you often forget because you don't normally have white space at the start of the line, but... Alright, so... that should be it. Right now we need to just fill in S, so... for now, we just want to look at where S is. Look at each neighbor. Okay, so... Alright, let's do it like this. For delta in... so it's going to be... We'll go up. So that's -1 row, 0. Go down. 1, 0. Go left. Go right. Just got to part 2. I got a place today. This is unfair in GML. Therefore, he's not on part 2 yet. Yeah, you don't worry about any spoilers or anything. I don't really care too much. Alright, so... okay, so we want to say delta R, delta C equals delta. Alright, so that's giving us the row and column modifiers. So we want to check neighbor equals, so it's going to be pause of animal dot, see, I could create an addition method here, but this might be the only place we ever use it, so then again, part 2, well, we'll see. So animal dot row plus dr, animal dot c plus dc. All right, so that's the neighbor. We want to check if g. So if animal in g.edges. So if the neighbor's outward edges contain the start, then we want to reflect that. We want start to connect back to them. Like that. So that should fill in the two. Okay, so now the graph is complete. So that was all basically prep. We've got the graph. Now we need to do... We'll do breadth first search. Run this maze through my visualizer, it's completely mad. Alright, we need to import Q. So I feel like we should make this a method because we might need it for part 2. So let's do define EFS from a starting location. So this is just going to find all the nodes reachable from this starting location and their distances. And return them. Should we return them as a dictionary of nodes to distances? This gives us more information than we need, but yeah, let's do this. Could be useful. So let's say dist equals start maps to 0. So that's the distance to each node. Q equals just an empty Q. Q.put start. Anything else? No? Okay, so while Q dot while not Q dot empty. All right, so this is the bit we need to think hard. So we've got the queue, we've got stuff in the queue, and in each iteration of the queue, we want to take an item out, and it's going to take them out in a queue style. So first in, first out. FIFO. And so current equals q dot get. So that takes out of the queue. Then we want to we don't need to do anything with this current. Except we want to look at its neighbors. So neighbors equals right for neighbor in. So it's going to be g dot edges current. And even if current was never placed in the graph, like if it was a dot, that's fine. It'll default to an empty set. That's the beauty of default ticks, no having to write any exceptions. Alright, so the neighbor in g.edge is current. So if neighbor in dist, skip it, because we've already found the shortest path to that. That's not really going to happen, but just keep this BFS as generic as possible. So this is if we've reached this point here, that means this is a new unexplored node. So we know what the dist will be. The dist of neighbor equals dist of current plus 1. And then just pop it on the queue. So this will just go until it's exhausted a chain. And then we just want to return the dist table. This gives us all the information of what we've found. Alright, so I should make sure this compiles. We haven't actually tried that at any point. Okay. Alright, so we want to run BFS. So let's say dist equals BFS from the animal location. Print dist. Alright, this is not... Okay, so pos doesn't have a printing method. Let's... Okay, let's make it... Let's give it a printing method just so that it can be read. How do we do this? It's going to be... like that. Alright, that's our dist table. Is that... looks... yeah. Looks good. So it goes into the 6,000s. 16,120. Could use recursion for this one too. Well, that is... recursion is essentially depth first search. Yeah. You can write depth first search in a recursive way too, but it's not a good idea because if it goes to 6,000, that's gonna get Stack Overflow. But but you can write depth first search using a stack where you have a explicit stack. That will stop you from using internal stack. In Python, I would just use a list for the stack. Well, recursion, well, it wouldn't give you the right distances though. Although you would, in this case you would, because it's a nice loop. In general case it wouldn't, because you wouldn't know if you could have reached a place from a different direction. Well, actually, yeah, because in depth first search here, if you go down a loop, you would just keep increasing distance as you went round in the loop. But then when you get back to start, you can just do some... You can pretty easily work out what the farthest distance should have been, just by dividing by 2 or whatever, and adding 1 as necessary. But yeah. Breadth first search gives us all the distances, which might help with part 2. Okay, so for part 1... what do we want exactly? We want the maximum. So it's going to be max of this dot values. Looks like it's going to be 6931. 6931. And this, so the point of breadth first search is it's going both directions simultaneously or in parallel. So it's not going to go around and it could go further than it would have taken to reach any node. So it's going to eventually meet at the farthest point, and that's why 6931 appears last in the dist, because it was the last thing to get unpacked from the queue, because it was going down both paths. Alright, 6931. So what exactly, how many steps along the loop? Yeah. Correct, okay. You quickly reach the farthest point of the loop, but the animal never emerges. Maybe its nest is within the area enclosed by the loop. Oh, okay. To determine whether it's even worth taking the time to search for such a nest, you should calculate how many tiles are contained within the loop. Interesting. Yeah, I can have a look at these links. So this one was a Marrow's one. Hang on. Wrong link. Oh, nice. OBS, I don't know if this is new, but OBS gives you a preview of image links as well, so you can see exactly what people are posting in your chat before you actually open it in the browser. So this is Umaro's one. Oh my. And can't really, okay, well I can zoom in using browser zoom in, but is that, what are these squares? Are they just like no pipes? Ah, okay. Oh, cool. Alright. So the actual loop, I guess, is... we can't really see from here, but I'm guessing it's around here, because... no, it's going to be further out. I'm guessing it goes quite far out. Alright, this is Smab UK. Oh, nice. Ooh. Interesting shape. So he's trying to make it as hard as possible to find the the inner area. Okay, I'm just trying to think what we need to do here. All right, so some ideas. So if I were to follow this loop around, okay, so if I were to start walking along my loop, okay, let's use this example here. You start here. Let's say we follow the loop from this path. But I were to kind of put my hand out to the right. So the area on my right will be inside the loop. And the area on my left, the space to my left, will be an outside. Unless there's no space there, because there could be a pipe there. So as I'm walking along, I can keep track of some nodes which I know are going to be inside the loop. Right. In particular, we'll find those two spaces and those two spaces. There won't be all of them though, because there could be like this. Oh. Oh no, this is outside. But there could be a big block, so we'll only get the edges of it. But that will give me enough knowledge for me to be able to then use breadth first search repeatedly from all those spaces to actually find the full space, sort of. How do I put this all together? So I had to just loop through the empty space objects and check if they were enclosed. Yeah. So you can start breadth first search from every space on the map, I suppose. And there will be one space, which is the outside, the biggest one. And every other space will be inside. As long as as long as you're not allowing yourself to ever cross this. Hang on, empty space is specifically a periods character? Is that what they mean? No, tiles contained within the loop. Wait. But it seems like it always happens to be period characters. Oh, okay, let's look at this one. These eyes are enclosed by the loop, and they're not period characters. Fine. Alright, so my idea really is just, so we've got our loop, right, defined. So we can start breadth first search at all the remaining nodes on the map until we've spanned the whole map across all our repeated breadth first searches. And when I do a breadth first search, even depth first search would be fine here, but we've already got a breadth first search method. When I do this, I'm banning myself from ever crossing the pipes that form my loop. So that's an obstacle now. So if I do that for every node in the map, precisely one of those should return the outside. So I'm allowing myself to cross any tiles as long as it's not our loop tiles. So you're allowed to walk on pipes, full stops, whatever. Just breadth first search. So this is, we basically need to write breadth first search again because we don't actually care about the edges now of the graph. This is just plain old 2D flood fill. So if I do that for every node in the graph which isn't on my loop, I should, precisely one of them should be the outside. Unless the loop actually gets really close to the edge. Or if that happens, then we'll figure out what to do if that happens. But basically, I just need to subtract 1, because only 1 will be the outside and everything else will be inside. No, that's wrong. Because they showed an example where this one here, that is outside. Okay, but it will get me somewhere. That will give me a bunch of spaces, some of them outside, some of them inside. It remains to work out which one's inside and which one's outside. Okay. So there is the classic algorithm for working whether you're inside or outside a loop, and that is you just take a horizontal line until you get to the edge of the map and you count how many times you crossed that loop. If it's odd, you're inside. If it's even, you're outside, because every time you cross, you go from inside to outside, or vice versa. So you basically draw a line to the edge of the map, you count how many loop cells you crossed, and if it was even, that means you either, you never crossed it, or you crossed it twice. That means you went in and out, or you went in and out and in and out, and so on. So that's the inside a polygon algorithm. We could do that pretty easily. I mean, you can do that. We don't even need to do flood fill. In theory, you could do that for every cell in the map. Would that be too expensive? Not really. Because we process the whole map. So basically, it's linear time. It's basically the whole map multiplied by 1 length of a list. Should we just do that then? I think we'll just do that. I don't think it would be too expensive because the map is small enough. But if the map was just too big, that would make which would make it in the billions or something. Then we would have to do probably flood fill to reduce the to split it up into components and stuff like that. And for each component, we take one representative cell and work out if it's inside or outside. Okay, let's just do this slow way then. No flood fill. So ended up flood filling in the end. All right, let's see where we can get with this. So I want to take every. All right, we want to define a method. Is inside. We want to supply one pause and a loop. The loop is going to be a set of cells to avoid. They define the loop. Alright, so if we're doing this, we kind of need to know. And you can also walk to the nearest edge of the map. You don't always need to walk to the right, but whatever, let's just walk to the right. Okay, so if we're doing this, we need to know how big the map is, don't we? N. Is it square? Well, we should do this in code anyway, so J, I don't know if I'm doing this right, but let's say m equals j plus 1. So whatever the last j was, the actual width will be m, and the actual height will be I plus 1. Let's try that. So we want rows, columns. $140, $140, yeah, okay. We've got n and m. Defined. So we want to use n and m. So I want to say, yeah, 140 is pretty small. So okay, so we basically want to add columns until we get to 140. So for j in range, so we go from 1 up to and including 139, I suppose. Well, no. Hang on. It's going to be 140 minus. No. Let's do this. Starting from pos dot column plus 1 and finishing at the edge of the map. Switching streams now. Good luck. All right. Thanks for coming. Smap UK. Yeah, I'll probably raid Captain Code and then afterwards we'll see how long this takes me. J in range. So I'm changing the column. So let's just say new pos equals pos dot row j. All right. So new pos is this. In fact, you have subtitles. I'll just make you quiet and loud. Yeah, I'm using an OBS extension, which I recommend. It's called Google Captions, so it's using Google's API to get subtitles. It's pretty good. New pause. Is that? All right, so we want to count how many times we cross the loop. So if new pause, including if it's the final element, because that's the final bit we use to get out of the loop. Okay, if new pause in loop crosses plus equal 1. Okay, so at this point we've counted how many times we've crossed the loop. We have to make sure we don't start on the loop. So then this is well defined. Okay, we say we're inside, return crosses %2 is 1. We return true if it's an odd number. All right. So now go through every cell on the map. So total equals 0. So for I in range n, for j in range m, pos equals pos I j. So we need to extract the loop. So loop we got from dist. So loop equals set of dist dot keys, including the starting point. So that's our loop. So if pause in loop continue, we don't want to start from a loop location. Alright, so now we're on a non-loop space, and it doesn't matter whether it's a pipe or a full stop or anything. Everything outside the loop might as well be a full stop. You could actually do that. You could just replace your map with full stops. That's one way of cleaning this up. It doesn't matter here. We want to see, so total plus equal is inside pause loop. Is that it? That's quite simple, isn't it? Almost deceptively simple. 1463? Let's think. So yeah, if two pipes get close together such that there's no inside, then that's fine. Nothing would happen. Feels like it could be right. Much higher than yours was. Alright. Let's see. Nope, it's too high. Okay. Gonna have to try the examples. Calculate the area within a loop. How many tiles enclosed by the loop? Alright. What could have gone wrong? So the is inside. So we start from pos.column plus ones. So we don't start from our current space, because we know that's not a loop anyway. And we finish at 139. We should really use M here. So the new pos will be same row, different J. If new pos in loop, crosses plus equal 1, and then we return. So 1463 is apparently high, which would indicate we might have included outside cells. Let's try counting the outsides. I'm just interested to see what the number is. $4,275. All right, so that is bigger. So it looks like we're including some outsides. Are we making sure to include every cell? We should be. Pause in loop continue. Yeah, we don't include. And the loop, yeah, includes the start as well. Don't see anything obviously wrong. Okay. Alright, let's try these examples then. They've given us a nice bunch of examples. Start with the most basic one. This one. Oops. Okay. So I should have written this to handle any input. It's good that I did that. All right. Try now. So, and this isn't even square. So yeah, 9 and 11. 23 is the size of the loop. 6. It says there's 6 insides. Nope. Should be 4. Where did I get 2 extra ones from? So it should be these 2. Alright, let's print them. Okay, so we've got 1020. What? So it's going to be row 1. So it says these 2 are inside. Oh, damn. I see. If you step... Oops, don't move things around. This doesn't work because if you step here onto this loop, you never actually leave or enter the loop. You just stay on the edge. But if you walk this way, this is crossing. This is not. Damn, can I resolve that? I mean, you can sort of... Oh, let's think. I mean, if you look at the type of pipe it is, you can reason it out, but then... So basically, if you've walked onto a horizontal, but then what about corners? Well, corners are also... Right, I probably need to take a couple of minutes break as well, so I'll have a think about this issue here. Alright, see you in a couple of minutes. Alright, so yeah, this is a... I don't see any easy way of fixing this if we continue with this approach. When you can look at... You can say... Oh, maybe there is. But basically, if you walk from one pause to another along an edge of the graph, then you don't count that one, do you? Is that just the rule? It is. I was worrying too much about the pipe type and corners and stuff, but actually, yeah. If you walked onto a pause... So basically, for each of these pauses that we're looking at... Oops, don't move stuff around. If we're counting it as a crossing the pipe, for the purpose of counting it as a crossing the pipe, it only counts if there is no, if there isn't a graph edge between the previous pause and the current pause. Then you can't have. Okay, let me write this in code, it might be clearer. Alright, so in this loop here, pause is where we've arrived. So basically we want to say hang on, so we're skipping any... Oh, I see. No, it's not that we're crossing in and out and in and out. We're basically skipping this whole bunch of things because we said if we're... Ah, then it's actually easier. Okay. I think what we need to do here is just keep track of whether we've actually crossed or not. Hang on. Oh, I'm getting confused now. So we're allowed to walk along the loop. Okay. We just count crosses if we make a step which doesn't follow the loop's track. So take this out. Alright, so we walk along the loop. If we want to. We can walk along an empty space, we can walk along the loop. But we count every step where we didn't follow loop edge. Alright, so... wait, no. This is not the bit I want to change. This is the bit I want to change. Okay, so... Okay, so if... So what is the rule? The actual rule here? Basically, if we step off a loop without following an edge. So if the last node was a loop cell, but it doesn't connect to the new cell, that is a cross. So would that work here? So here we get one cross when we step onto the F, and then no crosses. And then we get one cross when we step here, and one cross when we step here. So it'd be 1, 2, 3, 4, right? That's correct. So how do I say, so last pause equals pause dot j minus 1. Okay, so if last pause in loop and new pause not in g.edges. So it doesn't matter if we've stepped onto a loop or not. All that matters is if we've left a loop without following its edge, because that means we've either stepped into open territory or we've stepped onto another pipe, another section of the loop, but not the same continuous stretch of loop. So we're not following the loop. Okay, so not in g.edges. Last pause. Will that just work? Oh, now we got more. Hang on. So if last pause in loop and new pause is not an edge from the last pause. Oh, because... Why have we got more now? We're counting more as inside. Let's see what we're getting now. 1020. Okay, let's try and resolve this 1020 thing. So 10 is this space here. So we want to count how many times we leave. Ah, wait. If I go along here... Ah, I see. That's... I love how happy the demons look in the Doom cover art you used. Oh, you're using the Twitch VOD. And I'll give you the link to the... I haven't made the YouTube video live. Let's just do that, because the Twitch VOD won't look as good. And it's quite slow. Let me just make this one live. Okay. That's the YouTube video. Alright. Also, it'll be 1080p, so slightly higher res than the Twitch VOD, which is like 936p. Okay, so... Oh man, this assumption is just wrong, because if we enter this... I'm counting that as a cross. Okay, okay. What is the rule then? So in this case, we never make a cross. So then I think the rule is... the rule is actually rather simple. It's just if we ever cross a vertical line, because every other case, if we go along these, they don't count. Because we're not really crossed inside or outside. It is actually just if it's a vertical line, isn't it? So here, we cross one vertical line, another one, so we're outside. Yeah, it is just vertical line. Which actually means in our edge list it'll be north to south. Alright, so okay, so what do we write here? So if okay, we don't need a lot of this. We need if I'm gonna get rid of last pause. So it's if new pause in loop, and so it's going to be the north edge, so it's going to be pause of pause dot r -1 j in g dot edges new pause and so it's north to south crossing. That's the only, I didn't think that would be the only case we need to watch out for. I hope I've got this correct. Alright, so so we need doesn't like me doing it like that. There. Okay. Can I not put this on a new line? Do I have to remove the indent? Alright, just put it all on one line then, whatever. Oh, it's because I didn't, okay, Alright, is this correct? So if it's in the loop and it connects one row up and one row down, it's a vertical line. 5. Slightly better, but there's still a mistake. Alright, let's find, okay, so what, 5, 5? What's that? So it says this. Oh. Oh, fuck. Yeah, this doesn't work. Okay, there's got to be a more generic way of doing this. So, okay, we walk here, we enter the loop, the actual physical part of the loop. Then we walk here, we move, we exit the loop part, and we enter a new part of the loop. And then we leave, right? So, I reckon crosses, I think I'm getting it now. Stuck? No. Why do you think I'm stuck? If we enter the loop, that should count as a cross, and if we leave the loop, that should count as a cross, because that adds up, right? If we enter the top and exit the top, that's the same as if it was just like a tightly bound loop, and we crossed across both sides of it. So we should add one cross for entering a loop piece, and add 1 cross for leaving a loop piece. Alright, go back to what I had before. So last pause equals... Alright, so if we enter a loop, what's the easiest way to phrase this? Yeah, okay. We get two cases. If we enter a loop space. Hello, Songor. Okay. Handle the 2 cases separately. So if we... Alright, so if new pause in loop. Alright, what do we do if we enter a loop? If there was no edge between this space and the last one. Alright, so we should actually check here. So if the one case we don't want to count is if we're walking along a loop. So if new pause in loop and last pause in loop and G and last and new pause in G dot edges last pause, we skip that one. That's the one case that's throwing us off because we're walking along a loop. Every other case we either add a cross if we enter, add a cross if we leave. Okay, so if new pause in loop crosses plus equal 1, if last pause in loop crosses plus equal 1, that's kind of 2 separate pieces of loop that are being crossed. Now we got no insides. Wait, so hang on. So if new pause in loop and last pause in loop and new pause connects to the last pause. So that handles this case correctly. Okay. We're adding 2 for every cross. That's the issue. So in this case, what do I want to do? I want to add 1 for entering the loop. Oh no, what I said earlier was what I should be doing. So you add 1 for entering a loop from not being on the loop. Should we just add... Wait, if I would just... So if I take this one out, what does it do? that goes back to 7. Okay, so let's look at this case here. What do we want? We want to add 1 for here. We want 4. So we're already getting 4. The problem now is this one. So we what is the generic rule then? In this case, we add 1 for entering and we add 1 for leaving. So that's 2. In this case, we add 1 for entering, but we don't want to add 1 for leaving because then that doesn't count as a cross. I mean, there must be a much simpler way of describing it. It might be... So we can keep track of when we're on and off, right? So we go on, and then we go off. And we go on, off, on, off. So what is the difference here? I think the difference is here we went on and off, but we never really crossed. So it was like we just skimmed it and left. And here we did cross it. So I guess what we should be doing is verticals count as 1 cross. If I'd done the flood fill, I probably would have been done by now. Let's try and make this work, because clearly the logic is right in front of us. I just don't know how to word it. So, I think the rule generally is, okay, if you add 1 for going on and add 1 going for off, that's fine. But if we left a vertical line, maybe we should just not add a cross, because we never really followed its path, sort of. So if we just kind of compensate for that. So okay, so in general, we add 1 for going on the loop, we add 1 going for off the loop. But if we're leaving a vertical line, let's just subtract 1 to compensate, because we don't actually want to count that as a double cross. Because we would normally add 2 for those. We don't want to. In other words, we're saying if last pos in loop and it's not a vertical line, so let's say, let's just make a Boolean here. Last is vertical. Equals, so it's going to be we'll just stick with the new pos. So new pos is going to be -1 that's above in g.edges and +1. So that's is vertical equals that Boolean, right? So if new pos, okay, hang on, take this over here. So if new pos in loop and not is vertical, so we just ignore one cross in that case, but we'll still get the cross when we leave. Wait, is that actually right? It's better. So what is the one case we're getting wrong here now? 5 is this space in the middle here, isn't it? Wait. This space. So it's saying we're going on, that's one cross. Off, that's another cross. So so we're counting that as inside when it should be outside. So how many crosses are we getting here? So we always add one when we enter a non-vertical loop. So 1. And then we ignore these moves. So when we go from J to the vertical line, we add 1 for leaving a loop. Always. So we've got 2. But we don't add 1 for the vertical. And then when we leave the vertical, we add 1. So that's 3. So 1, 2. Oh, wow. Wow, yeah, I see the fatal flaw here. The one that is going to ruin us. This whole thing about entering the loop and leaving it without really crossing it. It only works if the corners are the same. If this corner went up, that would be invalid because that does count as a cross. Alright, I think I get the point now. It's a bit too fiddly. There's probably a way to make this work using this approach, but it's just too hard to work out when you're crossing the loop or not because of all these different types of corners. So maybe I should go back to the flood fill. Wait, is there one last ditch effort we can do to make this work? Not really, because when you enter a loop, you don't really know. What if you had last pause be... Right, last attempt. So if last pause was the time at which we entered the loop. Right, this is all overly complicated now. Let's say last pause. So when we enter a loop, all right, let's write this from scratch. Okay. So we've got a new pause, right? So we want so if new pause in loop, we want to keep track of where we entered the loop and where we left it. So entered equals hang on, we do want to retain that this thing here, but everything else we can get rid of. Alright, fine, we'll just put last pause just to make this loop work. Alright. Okay, so yeah, if we're walking along a loop, we don't want to do anything. That's still correct. But we want to say if last pause in loop, we want entered to keep track of, let's say entered equals none. Entered is the time we entered the loop. We want to have a look at that and see if they are the same direction or not. So if they're both the same direction, then basically we never actually crossed the loop. So that's not a cross. If they're different directions, then we did cross the loop. Sort of. So how do I say this? So we left the loop now. We entered here. And we left here. So when we entered, we want to see the different cases. So if entered was a vertical line, so if oh, I think I see an easier way of doing this. Okay. Exited equals last pause. So we have the place we entered the loop and the place we left the loop. And they could be the same place if it's a vertical line. right? So we have the place we entered and we have the place we left. What we want to check now is if one of these has a tail which goes down and one of the other has a tail goes up, then basically together they make a vertical line and that counts as a cross. So if, how do I write this? So let's just handle the separate cases. Tail up, right? So no, just say edge up. All right, so if all right, so just create two variables. Don't do it like this. Let's say edge up equals false. Edge down equals false. All right, just check both. For node in, just check both entered, exited. They could be the same, right? If pause, so it's going to be node.r -1 node.c, so that's the up section, in g.edges node, then there exists an up edge. And similarly, if +1 blah blah blah, then edge down equals true. All right, so at this point I've figured out if edge up and edge down, then we add a cross. That means we've actually crossed, where we're kind of treating the loop as if the horizontal sections are compressed so that it just looks like either a vertical line or just something which just touches our y coordinate but doesn't actually cross. It's really hacky, but that will count as a cross. Is that all? That might not be all. We might need to handle. So I'm saying if last pause in loop exited equals last pause. When did I entered is never set. Okay, so if new pause in loop entered equals new pause. All right, that means we haven't entered. All right, will this actually work? Take that out. Entered will get set every time we enter a new pause. And if we leave a loop, then we have to figure this out. God. 4. It gives us 4. So that works now on this example. Should we just go for the big one then? 325. It's much smaller. That's promising. Yay! Don't yay yet. We don't know yet if it's correct. It's smaller. That's good sign. Nope, it's too low. Curiously, it's the right answer for someone else. Okay, whatever. Yeah, that's too low. Alright, so now we're being... we're ruling out. Well, I guess if you sometimes happen to give an answer which is someone else's answer, it might... Well, that's interesting. That means it can, the right answer can go that low. Code Monk 325 is exactly my answer. Wow. Okay, so I solved someone's problem, but not mine. Oh, this approach is... I regret not going with the floodfill approach now. This is horrible. Alright, so we're skipping horizontal sections. Alright, let's try these inputs, examples that they've given us. So the first case, it works. Alright. Alright, how about the other example they've given us? And the correct answer should have been 8. So I probably... I don't like this approach anymore. Maybe we'll just start fresh with floodfill. Okay, so... Unless I can quickly resolve this, I don't think... 314. It says that's inside. 0, 1, 2, 3. 0, 1, 2, 3, 4, 5, 6, 7, 10, 11, 12, 13, 14. And that should be... Yeah, that's correct. Okay. So... And then the other 14... Oh, it's missing that one. It's missing this one. It's probably counting some others as inside. Yeah, this is a mess. The logic seems sort of correct though now. New pause, last pause. Alright, so if the last pause was in the loop, we have exited. Because if we just walked along the track, then we would have skipped that case. So that's where we left. Entered was set when we entered. So we've got the entered place and we've got the exited place, and they may both be the same place. And now we see if there's an edge up and there's an edge down. So for each of those nodes, if was node.c connects, then that's an edge up. And that's an edge down. And if we found both an edge up and an edge down, then we add one cross. Is that right? Because if it was no edge up, that would mean there's just edge downs. So we just kind of skim the top of a loop. And that's the only time we add crosses. I mean, I like that now, but apparently it's not correct. And with vertical lines, entered and exited will be the same place, but that's fine. I don't know. So we're missing this inside here. So what's going on here? Oh, I cannot decipher this. So this is L. So that's a corner, so it goes on. So that's 1 cross, 2 cross, 3 cross. It should be 3. 1, because these are condensed. 1 more. And then 1. But this is on the edge of the map. So we should go 1 past the edge of the map, because it didn't occur to me that the loop could touch the edge of the map, but of course it could. Of course it could. N plus 1. Try again. 8. Alright, that's right for that example now. Because yeah, you gotta give yourself a chance to leave the loop off the edge of the map. That's right for that example. Could that be it? Please? I feel quite confident with this logic now, even though it's not readable at all. 357, so it was just 2 off? No, it wasn't. It was like 22 off. Okay. So I feel like it's now correct, even though it's not readable at all. Oh, thank you. Okay, we got there in the end. So is that actually algorithmically more efficient than flood fill? No, it's not. It's actually less efficient because for each node, of which there may be a quadratic number, you have to do linear time to do that line. So it's actually cubic. Whereas if we did flood fill, that's the proper way to do it. That would be quadratic at most, because then you're creating a set of spaces, and you can work out which ones are outside or inside by just taking a walk along the loop and running your hand along the left. Or right. Well, you'd have to work out which is the outside to begin with. But once you know which is outside to begin with, then either it's your left hand or your right hand. Just walk along, and every space on the left, for example, is the outside. So you can mark all those spaces outside. It's also a bit tricky if you go down that approach. I don't see a way of doing this in a really easy way. 325 was your answer? Yeah, so... yeah, it thought I was logged in as CodeMonk. Alright, wow. I mean, it is a good problem. If you go down my approach, so that's the classic inside-outside polygon test. You extend an arc and you see where it crosses. but it's slow because it's linear time. But normally, when you're working out whether you're inside or outside a polygon, you would not check each space. Instead, you would just compute where your line intersects your polygon, which can be done in at most the number of edges of the polygon, but there's actually methods which will make it even faster, but if it's like convex and stuff like that. But you can do it in linear time using this method. You only need to walk each cell one by one and keep track of the crosses on the current row. So you're talking about, so you're still extending an arc like I did from each. Oh, I see. So because I'm starting from other spaces, all those crosses would also be crosses for like other spaces that I had done before in that same row. So essentially you can just mark as a Boolean every loop space, whether it's a cross or not, because basically every loop space we can mark it is cross, meaning if you come here from the left and you exit on the right, this is a cross. Yeah, and you can do that just by walking along the loop itself and looking left and right and just mark everything, whether it's a cross or not. That's a good way of doing it. And then from that point on, then it becomes really easy. So yeah, that makes it kind of equal in efficiency to doing flood fill. But flood fill is probably the cleanest one if you're separating everything out into lots of smaller methods. But then you got this notion of running your hand along the left or right hand side of walls, which is not hard, but it's just one additional thing to think about. I mean, one thing you can do is just take the leftmost loop section. Among all your loop sections, leftmost loop section. From that, you know you're on the outside, okay? So that quickly gives you a frame of reference. It quickly gives you where the outside is, where one piece of the outside is, because outside can be separated into multiple pieces. From that point on, walk along the loop, and you keep a tile which is corresponding to like the left hand or the right hand. In this case, it's always going to be left hand because well, it depends which way you walk along the loop. So make sure you walk along the loop in a way such that the outside is on your left. So as you do that, every cell you see on your left as you walk along the loop. So you have to remember, as you're going right and left really means up and so on, you have to kind of account for that. Every cell you see on your left is outside. Right? So from every one of those cells, well, conversely, everything you see on your right is inside. That's the thing we care more about. Okay, so you walk along the loop, you run your hand along the right. I'm just saying right arbitrarily, it depends whether you go up or down. And you keep track of all the cells you've seen on the right and put them all into one big set. And now you run flood fill from every one of those nodes, but you can kind of remove nodes from that set. So this is still quadratic time at most because you're not repeating any sections. That gives you all the connected spaces which are inside. because every connected space which is on the inside will at some point be touched by your hand as you're walking along this loop. Because they all touch the loop at some part, don't they? So, okay, how do I summarize that? You start from the leftmost point, because you know where the outside is then. You keep your hand on the inside, you walk along the loop, but always keeping track of what's inside. So that gives you kind of a run of nodes, which are, you know to be inside, and then you run flood fill from all of those to get all the other inside ones that you can't reach with your hand because your hand's not long enough. See, at that point, I don't even know what's the simpler method. That has its pitfalls as well. My one, this looks pretty ugly, but there's probably a way to make it cleaner. I mean, CodeMonk gave a good suggestion there. The logics will still be similar though, but we'll be running along the loop instead of from outside the loop. So you take a walk along the loop, and for every cell you work out if this is a cross or not. Yeah, it can be done. There's no... Yeah, I can't think of a method that I really think is super clean. Both methods have the tricky parts. Alright, it's pretty late. I need to go do stuff. So let's check out... This uses flood fill as one option, but is in C#. Okay, nice. I might have a look at that outside the stream. I think I'm gonna have to close the stream now. But let's have a look. Is Captain Coda still going? What's the username? Captain, oh, I forget the username. I'm not logged in. Captain... someone give me his username. Oh, I'm trying to find it in the Discord. The Captain Coda. Got it. The Captain Coda. Alright. Captain Coda's a pretty good coding streamer, and he is covering Advent of Code on a daily basis, so like me, but using C#. But he may switch to other languages, I don't know, but so far he's been using C#, so I highly recommend any viewers to head over to Captain Coda. I'm going to do a raid, and I've got to go eat because I'm starving, but I might stop by his stream just for 5 minutes as well. Alright, oh, I didn't really check all the stats and stuff. Doesn't matter, I can do that next stream. Alright, thank you everyone for watching. That was a tough problem. Tough because of the edge cases. Literally edge cases. Alright, see you tomorrow.